Okay, we will continue our discussions on switched reluctance motors. We have already covered considerably in the earlier lectures that switched reluctance motor is also a variable reluctance motor with saliency in both stator and rotor. Number of poles in stator and rotor are different. The poles will have to be even. It is typically 8 by 6, 6 by 4, 4 by 2 and such combinations. And you know that stator will have windings wound on the poles. They are not distributed windings, they are concentrated windings, they are like coils, and two opposite poles will have the same coil. So, if a 8 pole machine will have 4 phases, so the two opposite poles will be excited simultaneously. Then the rotor will have no windings. All the heating will be in the stator, mainly I square R loss, and of course, a little core loss because there will be fluctuating flux in the core in the stator. There is very limited heating in the rotor. Therefore, that way it is because there are no conductors on the rotor. So, no heating on the rotor, right. So, the principle of operation is you go on switching the different coils. So, that the magnetic axis of the stator will go on changing with time as you switch the different windings. So, as the magnetic axis changes its position, the rotor tries to align with that magnetic axis to get a minimum reluctance path, and then it experiences a torque in the process. At any time invariably one coil is excited, and therefore, there is a torque due to each of the coils. So, net torque, average torque will be the cumulative effect of the torque produced by different coils energized. So, we identified that inductance variation in space is critical. Each coil will have a inductance varying depending upon the rotor position. As the rotor is aligned, it will have a minimum inductance. When the rotor is unaligned, it will have a maximum inductance. And we also know that in the case of minimum inductance or aligned, the magnetic path invariably gets saturated. So, there will be saturation seen in the magnetization curve. When it is unaligned, there is more air, therefore, there will be less saturation. So, it is more linear. So, you will have a family of lambda I curves from unaligned to aligned positions. Okay. And we know that torque is proportional to I square into dl by d theta, right. So, it does not depend upon what direction you pass the current, it is I square. Therefore, torque is proportional to I square, that is where the I is the current flowing in the coil, and dl by d theta is the inductance gradient or variation of inductance with space, and dl by d theta must be positive to give you a positive torque. Therefore, you must pass a current at such an instant when there is a positive inductance gradient. So, a motoring occurs when you pass a current with a positive inductance gradient, and a generating or a braking may occur if you put it in the negative inductance gradient. So, the instant of switching of a coil is therefore critical, at what instant you switch the coil. Okay. And you must switch the coil at such an instant when it is picking up the variation in the inductance, right. Inductance should go for positive. Therefore, you must sense the rotor position, and at appropriate rotor position you must switch the respective coils. Therefore, rotor sensing is important for this machine. Okay. So, then switching the coil, and switch the coil to what? What do you switch the coil for? If you have a switching circuit, what will you switch? What will that, the coil will be switched to what? Switched to a voltage source. What is that voltage source? AC or DC? It will be a DC source. It is like a voltage source applied to a coil, and you expect even if it is a stationary coil, you know it will follow the RL circuit law, it will build up the current as a switch. But in this case the coil, there is a movement, and the RL circuit is okay so long as L is constant. In a typical RL circuit, current buildup will be when L is constant, but now L is also varying with theta. Therefore, you have a speed term coming into the picture. So, you have a differential equation in which the current is decided by that equation, which will consist of the resistance drops and the rate of change of inductance and the rate of change of current, both are important. Inductance varies with time, current varies with time. Therefore, you will have a buildup of current. Okay. So, ideally you would have got, you would like to have a rectangular current ideally, but it is not practical to achieve. Therefore, you will have I square dl by d theta will come to the picture. Now, normally for switching you use different type of power electronic inverters or converters. Okay. So, what it does is it goes on switching the different transistors to the respective coils to the DC source, right. And we briefly discussed in the last lecture what are the different practical configurations are being used, okay, for using this switching. You know the switching is basically that you must pass the signal to the drives of the respective transistors. Okay. So, nowadays this is all done through a microcontroller or a DSP. Okay. So, it is programmed in such a way it takes the signals and just passes a signal to the respective transistors to fire. Okay. And when if you want to switch it off, you all you need to do is to withdraw the signal, right. So, you are able to switch this. So, nowadays it is possible to have very high frequency switchings. So, that achieves the necessary controls. Now, you are also have to be concerned that it is not just switch it off instantly, you must also allow them energy, magnetic energy to dissipate slowly. So, you have freewheeling system also. So, the current will build up, then current is allowed to die down, okay. Then afterwards you do certain defluxing, the current will be brought to 0, right, because current cannot continue in the circuit long, because then it will be not desirable, because it may be flowing at a time where the inductance variation is not favorable. So, successive coils have to be properly switched by this inverter. So, this is also the issue. Therefore, switch reluctance motor technology will be centered around designing a suitable motor, designing a suitable magnetic circuit, designing the suitable poles, designing the suitable geometry of the stator and rotor, designing the suitable number of coils in the stator, okay, and then providing enough gap, air gap, okay, and designing the number of stator and rotor teeth, and designing a control circuit which will position, which will basically detect the rotor position and then pass the current, designing a suitable inverter, okay, which will have a DC supply. Invariably that DC supply comes from the front end rectifier, okay. So, there will be a controlled rectifier or a regulated voltage being provided. So, the whole system will consist of both the motor and a controller to the standard typically 3-phase supply, and this motor will be then driving to the required loads, which will be invariably variable torque, variable free speed loads. It can be a pumped load, it can be a compressor load, it can be a robotic load, or it can be any type position control loads, actuators and so on. So, you will see the total system consists from electrical system on the one side to mechanical system on the other side. So, it is a quite an involved technology which anybody, any engineer is expected to handle. Okay. And it is a combination of technology. You have electromagnetics here, you have electromechanics here, you have power electronics here, you have mechanical here. Okay. All systems have to be seen, and you need to have brutal signal processing of the thing. Okay. Now, let us with this background, let us see the configurations, practical configurations of VRM will have, we should have a low cost, and it must produce a torque, necessary constant torque, not depend upon the rotor position. It should provide the desired speed, okay. Then it should also provide high efficiency. These are some of the features that you expect in a SRM, okay. And it must provide you a very high torque to mass ratio. This is one of the quality parameters of such machine. It must produce high torque with minimum weight. Is it okay? So, these are the desirable features of an SRM. Okay. And of course, all this is repetition. It consists of a stator with windings and a rotor with no windings, but only saliency, and rotor position should be known to properly energize or switch the respective phase winding, which will produce the torque. Okay. I am just summing up the things. Okay. Then you have to sequentially excite the phases of a VRM, and rotor will rotate in step fashion. Now, of course, with high frequency it will not rotate in step, it moves, it rotates in as a smooth way. Okay. Now, you can also have a VRM with only single saliency also, right. You can see here the stator, there is no saliency. Okay. Now, it can still, supposing you have a phase 1, supposing this is the phase 1, if you excite this, then it will produce a axis here, magnetic axis. So, when this magnetic axis is there, this will try to align with this. Okay. And then what happens, the problem is when it is aligned with this, if you excite phase 2, what happens? Suppose you aligned with phase 1, if you excite phase 2, what happens? What happens? Is supposing you have excited 1 and this is aligned here, right. If I now I will excite 2, 2 is here, yes, okay. I will excite here the second one, I pass a current I2 here, this was the current I1. Tell me what happens. By 90 degrees will it rotate? Huh? No. For that?
If it is perfectly designed symmetrically, then it won't. If there is a 1 degree error,
it is 1 degree error. It will. There is a magnet which is lying here, except this, right. So, there is a problem here. Do you conceive this? If it is totally symmetrical here, so it is a magnet which is lying here, the rotor is lying here. It has nowhere to go. If you excite the second one, it will experience the equal torque on either side of the rotor bar, right. So, it has no way. If it is little inclined on one direction, then it will go either this way or that way. It can go down or it can go up. So, if you really want to work this system, what you should do? So, you should say, supposing if it is 1, then you just excite 1 2, then 2, then again 2 1, like that. That means you should have a combination, so that there is a magnetic axis which will move at 45 degrees. So, there is a 45 degrees switch step. Is it clear? In this machine it cannot be a 90 degree step, it can be 45 degree step. So, it can be in this position when both are excited, then you de-energize and you excite, this will come here, then you again both it will come 45 degrees like that. So, you will have a way to rotate this, right. And of course, this is doubly salient, here there is no problem. If it is doubly salient, so you have a this is a 4 by, it is typically a 4 by 2 system. And if it is the rotor axis is here at this position with reference to this. So, it depends upon, so if you excite 2, it will align with 2, if you excite 1, it will align with 1. Okay. So, you can again, of course, I think here also the same problem. So, it will have to be 1 or 2 has to be excited, right. So, it is again 1, 1 2, 2, then 2 1, 1 etcetera. Here also angle is 45 degrees, right. Right. I hope it is clear. So, there is another configuration, but you have coil, see earlier there was only a coil which was housed in slots earlier, here it will be wound on poles. So, you have this coil, in fact these two coil, see this 2 coil here and 2 coil here must be in series, okay. Then 1 coil here, 1 coil here must be in series. So, it is as good as you pass a current through this I1 and then it can come here, okay, then come out here. Is it okay? They are connected in series, right. And similarly, you can have the coil 2 which can enter here, come out like this and again enter here and come out like this. Is it okay? So, you have these 2 coils in series and these 2 coils in series. So, now the point is inductance variation with theta is what we are concerned about. So, stator wind inductance vary with rotor position, okay. Inductance is maximum with when it is aligned with the corresponding phase, when the rotor is aligned with that phase, minimum when the 2 axes are perpendicular or unaligned, okay. So, if you for this machine 4 by 2, if it is singly salient, you would expect that these variations will be like this. So, this will be L11 theta m and then L22, okay, and of course, L12 is a mutual. And if doubly salient, this will be L11 which will go like this and L22 which will go like this. You know that they are shifted by 90 degrees, is not it, because naturally they are shifted. So, that is how it will vary the self inductance as the for rotor position, this is theta m. Okay. So, this is how you plot the inductance with theta position, rotor position. So, you can find out the flux linkage is lambda 1, lambda 2, you know the standard L11, L12, L12, L22, L12, L21 anyway, all are functions of theta into I, this is the lambda, lambda is equal to Li, is not it. So, we say lambda is equal to L into I matrix, okay. L matrix is a function of theta, and the naturally that whatever happens to 1 happens to 2 after 90 degrees, is not it. they are shifted by 90 degrees. Okay. Whatever happens to 1, that is L1 L22 will be same as L11, but the instead of it will, while L1 is a function of theta m, it will be L22 function of theta m minus 90 degrees. Okay. Then L11 theta m and L22 theta m are self inductances of 1 and 2, L12 will be a mutual between 1 and 2. Okay. So, we have the mechanical torque will be delta W field by delta theta m, is not it, and well W field is a function of I1 I2 theta. Okay. The stored energy will be a function of the winding 1 current, winding 2 current and rotor position. That is how much energy is stored in the magnetic field. Here the magnetic field is mostly in the air gap, you do not expect any energy to be stored in the iron. Okay. So, this is W field dash, we call it as co-energy, which will be L11 I1 square, L12 I1 I2 and L22 I2 square. I think you are aware of this from the basic principle of electromechanics, right. Then mechanical torque will be a partial derivative of this, means during this period currents are not changed. Partial derivative means what? By mathematical definition, partial derivative means you derive it partially with reference to one variable, keeping the other variables fixed, not altered. Okay. Therefore, mechanical torque will be I1 square dl11 by d theta, I1 I2 dl12 by d theta and I2 square dl22 by d theta, right. So, it will be the, as you said, the inductance gradient is now important parameter for producing the torque. Okay. So, for doubly salient machine, dl12 by d theta is 0, okay, and mechanical torque is basically dl1 by d theta and dl22 by d theta. Okay. So, that is same as this. So, this is the torque developed in a doubly salient machine. So, therefore, the torque depends only on the magnitude of the phase current and not on their direction. So, we now have an expression for torque for a doubly salient machine, which will be basically sum of the I1 square and I2 square. So, the electronics which supply the phase currents can be unidirectional, right. You do not have to bother about the reverse currents. Current will be flowing only in one direction, right, in every coil. It will build up the currents, it will come down and so on. Okay. So, each switch need to handle only currents in a single direction. So, you have a simplification of the switch, it is unidirectional switch. Okay. This means the motor drive requires half the number of switches that would be required in bidirectional drive. Supposing there are drives which are bidirectional like inverters, then you require 2 switches, one on top, another on bottom. One for forward direction of current, another for backward direction of current, you need to. So, here it is reduced by half. Okay. Now, this is also another interesting variants of the VRM. Okay. This is this way it is called a CacheLated VRM, because you see this looks like a castle. What is done is rotor is having so many tooth, right, uniform tooth, right, and stator is having poles. Okay. These are the poles, say 1, 2, 3 or whatever it is, poles, but they are also cut in exactly the same way. Okay. Now, it is aligned, now one is excited, this coil 1 is excited now. So, this is the position in which the machine is there. Okay. You have seen the position now. means each of they are aligned, right. So, the respective tooth and tooth are all aligned. Now, you excite 2, what happens? This angle is beta, okay. Each of the slot and tooth angle is equal beta. Tell me what happens now? If one is de-energized and 2 is energized, anything happens or nothing happens? Huh? What happens? 2 will be 2 will become aligned, means there is a movement, right. So, there may be, it will try to align, okay, depends upon, okay, which way, either let us say, let me, it will try to move this way. So, it will try to align, these will try to get aligned, am I right? So, these will try, this will come closer. So, there is a movement of this, right. Then again next you, but then that movement is small, this is not moving by a pole, but it is moving by a slot, right. So, by this way, you can see that it is a smaller movement, okay. So, you may be, if you want like robots etc., where you get high torque and small movements, these such systems can be thought of, okay. In fact, even your cloth, the motor in your watch is also a sort of reluctance principle, incidentally, okay. It has to move 1 step per second, okay. That is what it is. It is a reluctance mode, right. It is a quartz which will, that cell is going to have the signals to go, okay. And next this may get aligned, okay. Is it okay? So, you will see this CacheLated VRMs will have a movement which is smaller, okay, by this amount, okay. Supposing you have a 6 poles and 4 tooth per pole, we have 4 tooth per pole, 4 teeth per pole. So, there will be 28 rotor poles, okay. Now, in such a situation, each stator pole has been divided into 4 sub poles, each stator pole divided into 4 sub poles by addition of 4 teeth of width, this is beta, that is 45 by 7 or something, okay. The same tooth slot spacing is chosen for the rotor, resulting in 28 teeth on the rotor, okay. So, with this we have a subdividing stator and rotor into teeth is known as CacheLated VRM. So, beta were chosen so that when the rotor teeth are aligned with those of the phase 1 stator pole, they are not aligned with those of phase 2 and 3. So, you can see how much angle will be there, you can calculate. By each switching, how much angle it will move, that you can calculate by the respective differential. It is like a Vernier principle basically, okay. So, when the excitation of phase 1 is removed and phase 2 is excited, rotor will move by this angle 2 beta by 3, okay. You can find out, you can calculate what it is, sorry. Okay. Now, the CacheLated VRM can be used at low speeds and high torque for the stator, given stator power input. They are basically for such applications, okay. Use of more teeth can increase the position resolution of these machines. I mean, resolutions are good, because you can go a very accurate low positioning. So, it is basically for position control. This is a requirement in several applications like robotics, mechatronics, machine tools, etc. Okay. Right. Now, let us look at little more detail. I take a typical 6 by 4 machine, and 6 by 4 machine, we have a inductance variation. I have say minus 40 plus 40, then 50 or like this, right. This is the typical variation. I have a 6 by 4 machine. Okay. So, we will say that typically this is the variation of inductance for one phase 1. Okay. Then phase 2 is shifted, okay, by 30 degrees. Okay. So, instead of here this is 0, you have variations say from okay, this is 0, then 10, sorry 20, it is not very this thing, and it goes up to 60. Each one is, it will follow something like this. And similarly, you have from whatever was happening here, it is happening after this 60 degrees here, and then this this one will move, it will become, I think this is minus 30 or something, minus 30, and okay, I think it is minus 70 or something. So, write down typically a, this is for phase 2, and similarly for phase 3, I mean it is a shifting by 60 degrees basically. Okay. Phase 3 will be okay, this is starting from minus 10, to plus 30 or something. Unfortunately, they are not in proper scale, you have to bear with this. Minus 20 goes like this. Okay. Okay, each one is 40 degrees, minus 20 it goes to minus 60 or something. Minus 100. Okay, I have written broadly the inductance profile of 3 phases, phase 1, phase 2, phase 3. And when do you excite each of the phases? What instant? What is the instant you would like to excite? What will be the current waveform you would like to give ideally? What instant you want to excite phase 1? When the rotor position is minus 40. Okay. Therefore, let us say that that is at this instant, and then dl by d theta. So, this is what you would like to give, am I right? I and dl by d theta must be same. and which what time you will excite this, you would excite something like this, no, here and maybe here, okay. Is it okay? You would like to excite it here, right, and that will, so this will also be dl by d theta which is also proportional to torque, right. And similarly you can say this third one you will excite somewhere here, right, and somewhere here, okay. This will be the, so you can say this also T1, T2, T3. After all, this is the torque that is experienced by the rotor, right. Okay. Now, what will be the net torque now? If this is the, after all, this is with reference to different position it experiences different torques. So, what will be the net torque? If you sum it up, how does it look like? Please do it. Just sum it up in one scale. So, you may find that there is a, will it be continuous? It will be continuous, okay. Let us say how will it this be? Supposing this is somewhere it is coming here, but there are some overlap periods where there will be a peak here, is not it? And again, you know, then this there will be some peak here, okay, right, there may be some peak here like this. So, you will find broadly that your torque versus position, if you do like this, so it may have a is not it, this will be torque versus theta, right. I mean just a demonstration. What does it imply? There is, what does it imply? This all leads to torque pulsations. You will notice there is a torque pulsations, right. So, ideally what you should do is you make sure there is no overlap. Ideally, if you want to have pure positive steady torque, constant torque, what you should do? You should have no overlap. Is it clear? So, what we are trying to do is, if you ideally neglect saturation, a pure smooth variation inductance, I push a like a brick of, like a your ice cream you have bricks, you know, you put a brick of current, okay, brick of current, place it in the respective coils nicely. So, this is what it is, but nothing happens ideally, right. So, you are bogged down with problems, because so the problem is current not a rectangular brick, right, current does not go like that, okay. So, how does, you know, invariably your current will be, what will the current be? You know, if you only apply a voltage, so you would expect your current will go like this, okay, when you apply a voltage, then it will freewheel like this for some time, then you do defluxing and it may again go like this. So, this will be the thing, right. So, there will be a current in the coil beyond, you know, this. So, what time you have this on, what time you have off, what time you have the freewheel, again that matters. Sometimes what they do is they will excite it even before, this is one option. See, if you want to pass a current here at this instant, is not it, then do not do it at this, but do it a little early. So, that by the time it comes there is enough current which has built up. This is also one of the things. So, it is a lot of intelligent strategies we have to think of in exciting the coils, right. So, therefore, the inverter logic is important. Is it clear? So, that means what time you switch the transistors or the switching devices, what time you switch it off is important. So, that there is a good amount of energy which is pumped in to the coil. I do not know what is inverter giving, it is pumping energy to the coil, is not it. Okay. Next issue problem is you have the what is the governing equations. What are the governing equations? You have any coil, jth coil will be Rj Ij plus d by dt of lambda j, is not it. Okay. And what is lambda j? Will be equal to its self inductance which is a function of theta into Ij. Therefore, you can write down Vj will be, you are aware of this thing, Rj plus d by d theta of Ljj, okay, into omega m, the speed, into the current Ij plus its self inductance into d by dt of Ij, right. So, this is a governing differential equation, so you have to solve it, and you see the Ljj is also function of theta, is varying with theta, okay, and therefore, you need to solve this equation, okay. And then of course, then torque is half of I square dl by d theta, the developed torque. So, this after finding the current you find I square and also multiply with the respective dl by d theta, each are functions of theta and time. So, you have to solve these equations. So, normally nowadays numerical methods and you can use this some of these modules which are available, okay. So, typically if you solve any equation, suppose if say omega m may be constant, then there will be you have to solve for when V is switched, one equation, when you apply a V is switched. So, you have one equation, then V is off, the freewheeling, this is another equation, right, and you have V may be negative, defluxing, you want to kill the flux, maybe you want to make sure that the current dies down to 0 at a predetermined time, okay. So, you may have to solve for V equal to some minus V or something like that. So, you have to have a equations to solve. So, there are some numerical method examples given in the textbook. So, you can see that. So, typically you can have a picture of current which builds up, okay, 0 to when you apply a voltage V, and it can also die down if you apply minus V, right. And one of the equation here, you can I1 will be some constant T divided by some constant k 2 plus k 3 T, no some so many amperes. Okay. So, I mean again this is a question of solving the equations, I am just giving you one idea. Okay. So, they will all be functions of this is one of the procedures, of course, because of limitations of time we can't go to the thing, but I think you can read through, you are aware of differential equation solving. Okay. Then last aspect which we wanted to discuss is, you are aware that there is a lambda I variation which will have a two extremes, say for different theta m, let us say 0 to 90 degrees, and which is aligned, which is unaligned? Unaligned, this is aligned, okay, and you will have a family of curves in between like that. Okay. This is what you will have. Okay. Now, what will be the your current is what? Current is starting from 0, going to some value I, continue in that value, okay, then come back to 0. This is what your trajectory. See, you are pumping in a current. No? So, you can clearly see, supposing a linear region, okay, then you are having a taking it to the current goes here and comes back here, right. This is linear, this is the path, is a trajectory. Is it clear? Your current, what is the path it will go from 0 to respective current and go to the respective theta position, etc. Other way is, if it is saturated, then it goes here, actually it is sorry, it will be, it will follow say unaligned, then it will go and then come back here. Okay. This is saturated. You are passing a current, it is in unaligned position and it pass and goes to aligned position, okay, and that is the path it will follow, right. So, it is as good as, in this case we can say it was unaligned, you have a constant current and you go here and come back here, is not it. As the current traces through, what is the respective magnetic paths it will follow. Okay. Now, what is the okay, I will take 5 minutes 20. So, what is the power input will be IV, which is I d lambda by dt, is not it, and what is the net work done will be power input integrate, okay. So, that will be I d lambda, okay. So, in the this will be, this is the lambda, sorry, this is the lambda, this is I. If we integrate, this will be the net work done, this area. In the process, you have put in some power and that is the net work done. Okay. Then what is the peak energy given by the inverter, which is 0 to lambda max, because peak energy is whatever it has already pushed into the maximum into I d lambda. Okay. What is the, how much energy which has given by the inverter in one stroke, okay, and that will be this whole, if you took the area, this is lambda max, this whole thing is the total energy, that is O A B C. So, O A B C O is the energy from inverter, okay, and O A B O is the work done, okay, and the remaining one, this is energy that is retained. It is basically called, you can call it W field or whatever it is. This energy, that is O B C O, is the energy that is returned, okay. So, from inverter certain energy is given to the machine and then certain work is done, we neglect the resistance, okay, certain work is done, but this whole thing is, after all, when you have a magnetization demagnetization of the coil and iron, so it is a question of taking energy and giving back energy to the system, okay. So, you have this these two things into your calculations, okay. So, we have the inverter rating over the net output will be that area, total area W field plus W net over W net, okay. This is a quality factor. That means what should be the size of your inverter, because inverter has to give you the maximum flux, inverter has to give you the maximum flux and maximum current, right, and that is the size of the inverter, and what is the work done is what you have the net output of this, okay. So, if you have some stroke like this, okay, and you will notice that if it is saturation is there, if there is a saturation, require less inverter rating, because this rating, if the saturation is more, your this rating is less. If it is goes to the straight unsaturated mode, then your it will become more, right, and this work done is a ratio basically. Therefore, the points that we need to understand here is what will be the ratios if it is saturated with unsaturated, okay. Therefore, the few points which I want you to note is, one is this quality factor is smaller with saturated machines, okay. Then design is a trade off, because you have a trade off between whether you want a saturated machine, okay, or an unsaturated machine, okay. Then saturation tends to increase size of the machine. This is one of the points. Saturation tends to increase the size of the machine, right. Then high saturation needs low power inverter, lower power inverter, okay. Therefore, the to summary is, the design of VRM is a trade off between size, cost, efficiency of VRM plus inverter. Okay. So, these are some of the factors that you need to address, okay. And you are aware that the critical issue is how, what path that it will take in this lambda I curve, okay. And you can choose if it is, it can be like this ideally, or but in practical cases if you have a aligned aligned and unaligned, in actual practice what the route it will take will be, it may have some current will not be constant. You please understand that current is not constant. So, it might follow some paths like this may be a practical path, because your current is changing with time even in the whole process, right. Therefore, your energy ratio is important, what we call it as energy ratio, okay, right. So, we will stop this. Of course, we can't cover everything on SRM in a with a limited time. Whatever I have covered in this is only to give a gist of what are the salient issues of SRM. Of course, there are a lot of things you can refer to in the literature. Anyway, I request you to go through the books and get a better idea of the whole sequence. We will close it here. Thank you.